Hyperstealth's laser splitter might turn conventional aircraft into low observable stealth. Hyperstealth's laser splitter could be used on conventional military aircraft to create a laser cone around the aircraft during flight to produce an air-ion barrier to radar, absorbing the radio signals to reduce the radar return below the threshold of typical adversary detection. Studies have shown that femtosecond laser pulses with a wavelength of 950 nanometers will create nitrogen ions. This could help countries keep the costs down as they look to modernize, but unable to afford the latest stealth aircraft, instead going with proven fourth-generation aircraft and adding on Hyperstealth's laser cones to reduce the radar cross-section, RCS. Hyperstealth now has 6 country patents issued for their laser splitter technology, which includes the United States, and 4 more country patents approved awaiting official grant status. This technology can split a single laser into hundreds, thousands, and even tens of millions of smaller lasers and even shape them into a cone. The potential to integrate this into LiDAR, lasers that operate like radar, could allow for ultra-high-resolution LiDAR at a theoretical 2 trillion pulses per second, which is 200,000 times faster than the fastest LiDAR. The material combination used in the patent only adds a few millimeters to the end of the laser, and the cone shape could remove the need for spinning the laser with a rotating mirror. This could allow for detection of stealth aircraft and submerged submarines up to a depth of 400 feet. Guy Kramer is the president and CEO of Hyperstealth and inventor of this technology. He now has 46 patents to his name, 43 in the field of physics, including a light-bending material, which can make the object behind it invisible. Guy believes Hyperstealth's laser splitter might be able to be used on conventional military aircraft to create a laser cone around the aircraft during flight to create an air-ion barrier to radar, absorbing the radio signals to reduce the radar return below the threshold of typical adversary detection. The ability of air ions blocking radar and even communications has been known for decades. With the launch of Sputnik, the first satellite, U.S. tracking was thrown off as Sputnik was flying through the ionosphere, creating a plasma shell around the satellite. When spacecraft returned from space, communications become blocked for critical minutes due to the ionization created between the atmosphere and the craft, enveloping much of it in a bubble of highly charged particles, cutting off communications to or from the craft until the charged particles dissipated. Some solutions have been found with satellite communications from above to antenna located near the upper part of the craft where the plasma is weakest. Aviation Week and Space Technology magazine, issue January 22, 1968, has an article titled Northrop Studying Sonic Boom Remedy, where Northrop discussed the use of electrical forces to condition the air flowing around an aircraft at supersonic speeds to potentially lower drag, reduce heating, and soften sonic boom. Air molecules ahead of the aircraft would be ionized, probably negatively, through a corona. The nose of the aircraft would be charged to the same negative potential, forming an electrostatic force field which would tend to repel or alter the course of the molecules as the aircraft approached. Limited wind tunnel work has established that the corona discharge readily propagates forward in a Mach 3 airstream with no measurable attenuation due to the airflow. Northrop officials concede that communications problems would arise in a charged aircraft, but pointed out that a solution might be found in the method used to maintain communication through the plasma sheath of a spacecraft during re-entry. In a possible application of the technique, the nose of the aircraft would have to be insulated from the rest of the vehicle to preclude charging the entire airframe. The excess electricity could be discharged through a trailing boom into the slipstream, which would act as a ground. In the March 9, 1992 edition of Aviation Week and Space Technology, an article titled Black World Engineers, Scientists Encourage Using Highly Classified Technology for Civil Applications was published. The article discussed potential deep black programs that may be unnecessary now that the Soviet Union had disbanded. One technology discussed in the article connects with the previous 1968 article, thermal signature masking technology, which is used on the B-2 stealth bomber, an engineer said. Basically, it's an electrostatic heat transfer phenomena that charges the jet engine exhaust stream to disperse the heat by a factor of about 800. It does a remarkable job of altering the thermal signature. He said the same basic technology, used in wing leading edges, can reduce a flying vehicle's radar cross-section, RCS, by masking thermal signatures created by aerodynamic perturbations of the air. The radar signature of an incoming warhead can be reduced to less than 10% of its normal value, the engineer said. We found that radar cross-section had a lot to do with aerodynamics and turbulence past certain speeds. If the black world actually has developed feasible ways to reduce airframe drag substantially with controlled electrostatic fields, commercial aircraft manufacturers and airlines should be campaigning mightily for the technology. The potential fuel and cost savings for just American, United, and Delta would be staggering. A scientist said other, more dramatic, classified technologies are applicable to lasers, aircraft control, and propulsion. However, the scientists and engineers were especially hesitant to discuss these projects. One said they are very black. Guy has helped NASA JPL with a classified program that involved air ions involving aircraft. He was asked to provide research, which took him a few weeks to compile, that JPL later said saved them between 10 to 15 years of research they would have needed to do it themselves. Now, Kramer believed his newly patented laser splitter, which he has assigned to Hyperstealth, could be used to provide a shaped cone or a series of cones, which could be used to vibrate infrared lasers at frequencies that induce air ionization during flight, thereby reducing the RCS or radar cross-section of the aircraft, even though the shape is not considered 5th or 6th generation stealth. These laser cones could be focused from different parts of the airframe to allow the nose cone, which houses the internal radar, to stay out of the immediate air ion field concentration being generated by the lasers. Laser cones may also be pointed towards the back of the aircraft to charge the engine exhaust to reduce the heat signature. The infrared or IR signal should be minimal, as the aircraft itself is not being lased as the laser cones surround the airframe. The lasers are also quite small and would be difficult to see in night vision until you were very close to the lasers. The Lockheed A-12 Oxguard, developed for the Central Intelligence Agency, the predecessor to the U.S. Air Force SR-71 Blackbird, experimented with a cesium-laced fuel additive to dramatically reduce the radar signature of the plane's massive engine exhausts and afterburner plumes by creating an ionizing cloud behind the aircraft to help conceal its entire rear aspect from radar waves. A reduction in radar cross-section, or RCS, also results in a proportional reduction in detection range, allowing an aircraft to get closer to adversarial radar before being detected. This potential to encase an aircraft in a controlled air ion or plasma envelope may also reduce drag and increase fuel economy and range, thereby allowing for dual use on commercial airliners and commercial aircraft where RCS is not required but limited laser cones on wingtips, the end of the tail and tail stabilizers and/or exhaust to reduce drag and potential turbulence, while also increasing fuel efficiency and range. As the larger aircraft parts are not within the cones, the radar cross-section reduction should be minimal. Naval applications could also be used on nuclear aircraft carriers where there is excess power generation for the ship's requirements, or any other surface vessel that has the necessary power. Hyperstealth now has 43 patents granted with 769 claims in the field of physics, with 5 more patents approved with a further 92 claims awaiting formal granting.